When using robots in crop harvesting applications, one of the most important components during the process is the gripper that will come in contact with the crop. It must be strong enough to pull the crop and at the same time soft enough not to damage it. Conventional rigid grippers are not suitable for this application as they tend to damage the crop. One solution is to change the rigid grip for a flexible one that allows to adapt to the geometry of the crop without damaging. However, there can be a wide variety of specific strength requirements for the different types of crop. These specific requirements can be obtained by modifying the input torque of the gripper or by changing the geometry of the flexible grip to a more or less flexible one. My gripper proposal avoids having to use these options. It consists of an assemblable mechanism that is placed over the existing gripper of the robot and can be adapted to different sizes and force requirements by varying some of its adjustable parameters. Let's see how it works. First, the grip width can be easily modified by sliding flexible fingers. The added mechanism, together with the robot gripper, forms a 3 degrees of freedom mechanism where the sliding sub-mechanism allows to adjust the orientation of the flexible fingers without affecting the position of the original gripper. Once the desired orientation is achieved, the sliding sub-mechanism is fixed and the complete mechanism becomes a 1 degree of freedom mechanism. This allows the closing motion to be transmitted from the robot gripper. The gripping force of the flexible fingers can be modified by adding a contact element to the mechanism. This element comes into contact with the blade of the mechanism, restricting its movement and converting the 1 degree of freedom mechanism into a 0 degrees of freedom structure. Now, in order to achieve the gripping movement, it is necessary to produce a mechanical elastic deformation in the blade. The stiffness of the blade will depend directly on the position of the contact element. Lower stiffness when the contact element is at the bottom, and higher stiffness when the contact element is at the top. And what happens with the orientation of the flexible fingers when we modify the gripping force? When there is no contact device and the force is completely transmitted from the robot gripper to the flexible fingers, these are designed to be parallel at the end of the movement. Now, let's see what happens when the contact device is placed in a high stiffness position. At the end of the movement, the flexible fingers end up with a certain angle. This may be desired in some circumstances, but suppose you want to keep the parallel position. This is achieved with a slight pre-adjustment of the orientation, and so we can get the flexible fingers to be parallel at the end of the movement. In general, the proposed gripper has the ability to adjust to a wide variety of size, orientation, and gripping forces to suit specific crop types.